But now let's move on to the next talk, and let me introduce the speaker. So Michael Schlottke-Lakemper is here. Yeah, he's behind Trixie.jl, so you might have heard of that package, active in the GUI HPC community. And he will talk about secure numerical computations. And yeah, the stage is yours, Michael. Take it away. Oh, and before I forget, because we didn't have time to rehearse this, 5 minutes, 2 minutes.
2 minutes, all right. Thank
thanks.
you very much, Carsten. Welcome, everyone, to my talk on secure numerical computations using fully homomorphic encryption. I'm Michael Schlottke-Lakemper, and I'm a computational scientist. So if you are expecting a cryptography talk, then I have to disappoint you already. So this is not going to be a cryptography talk. I will look at all of these, or many of these things that we'll be talking in the next couple of minutes from a computational scientist point of view, from an application point of view, and I will try to put in a little cryptography, but I will keep it to a minimum. Before I get started, let me first acknowledge my student Arseniy Kholod, who I've been working with over the past couple of months on this project. It's a side project at the moment, but he did really a great job, and a lot of the results we're seeing today were obtained by him. Also, there's a reproducibility repository that also includes the slides for this talk and all the code that was used to generate the results. So if you want to check this out later, you can do so. And the slides are also on there as well. All right, so data security, maybe some motivation. Data security and privacy is all the rage nowadays. Everyone has probably had some contact with it. Security and privacy are two related but slightly different things. So with security in general is meant that you prevent unauthorized access, so on a technical level maybe, whereas privacy is the concept of you don't want to share more of your data, more of your knowledge than you should have to. And examples where this is particularly important could be, for example, health data, financial information, or proprietary algorithms. And in general, this concept of data security and data privacy is a major challenge for cloud computing. On the one hand, you have the desire to keep your data private, of course. On the other hand, maybe the data needs to be processed in the cloud. So there's a challenge. On the other hand, you maybe have some algorithms that you want to use and apply to users' data, but these are part of your company's intellectual property, and you don't want to share them with anyone. So you also need to keep your algorithms private. And the concept that sort of tries to resolve this is called zero-trust computing. So basically, you don't have to trust someone with your data, and the algorithms provider don't have to trust you with their algorithms. And fully homomorphic encryption is basically an idea or a concept that tries to get there. So I talked a little bit about privacy, about security. So here's a very naive idea, and of course you know where this is going. So what if we want to do computing in the cloud, but instead of sharing our true data, we're only going to share our encrypted data with the cloud? So here's a very simple example. I have the numbers 2 and 4, and I want to compute the sum of them. And I want to do this in the cloud, and I want to do this in a way that the cloud provider does not have any knowledge about the numbers I'm trying to add up. So a very naive approach would be I add basically a random secret only known to me to each number. So instead of 2, I'll get a 7, and instead of 4, I get a 12. And I send these numbers 7 and 12 to the cloud. I let the cloud provider do the addition. I get the 19 back, and then finally I can retrieve or get the real result by sort of reversing this encryption, this very naive idea of encryption. So while this is technically secure, right, the cloud provider will never see the actual data, there are, of course, some problems with this approach. First of all, it requires local knowledge about the exact algorithm that's going to be performed. So if I use this approach, I have to know what the algorithm is doing to basically reverse it on my machine. So this already violates the first principle of this zero-trust computing. The second problem, of course, and this is a much more glaring problem, I think, is it does not save computations, right? I mean, this was a very simple example, but we can already see that I wanted to add two numbers, but now instead of adding two numbers, I have to add a random secret and then send it to the cloud, and then I retrieve it, and I have to do reverse the addition again. And it gets even worse if we go to something as simple as a multiplication. Now I actually have to do many more computations, so obviously this approach does not scale. And this is now where the concept of homomorphic encryption comes in. So the key idea is to be able to perform computations on encrypted data and getting results identical that are identical to what I would get if I would do the plain text computation. And the data and the algorithm is mutually unknown. So we get this zero trust computing concept. And ideally, and this is why sometimes you see fully homomorphic encryption. The fully refers to the fact that I have an arbitrary algorithmic depth of my algorithm. So here's a small visualization just to make sure that the concept is clear. So as a privacy-conscious person, I have all my data encrypted, and the usual way, if I want to process it, would be now I have to decrypt it. I hope one can see the mouse, yes. Then I have my data in an unencrypted state. I can process it. Then I have some function of data, so my result. And then, because I want to keep it secure again, I encrypt it again, and then I have my encrypted result. And the idea of homomorphic encryption is that I can basically avoid this detour over the encryption and decryption and encryption process and just have my encrypted data directly be processed and get to the same result in the end. Now, of course, if it were simple and easy, then everyone would be doing it by now, but many of you probably have heard about this for the first time in this talk. So there are some drawbacks, and some of them are very severe, and I will be talking about them today as well. First drawback, I would say there are limited basic operations. I will talk about which one that are available to construct algorithms using homomorphic encryption. So that means you have to rewrite probably most of your programs. The second one, drawback is the considerably increased resource requirements. As a computational scientist dabbling in the HPC world, this is, of course, a big concern for me. And the third drawback is the possibly reduced accuracy for your computations. All right, before we go into more details, here are some very high-level fundamental concepts of fully homomorphic encryption. Again, be aware that I'm not a cryptographer, so please don't use this and hide your new startup's great ideas and then come complaining that someone stole it. So full homomorphic encryption usually is based on asymmetric, so public key encryption, similar from what we see when we use PGP, for example. There are different schemes. They're all basically named by the initials of their authors. So there are some schemes for integers, there are schemes for real numbers, and this is the CKKS scheme, so by Chon, Kim, and Song. Is actually the scheme that I will be discussing today. Mathematically, it's based either on lattices or on the ring learning with error problems. If you want to know more about this, please don't ask me too much about it, because I'm not an expert on ring learning with errors. But it is said to be both of these, the lattice-based and the ring learning with errors problems, are supposed to be quantum hard. So some proponents of fully homomorphic encryption also propose it as an idea for post-quantum security. The key principle is in all of these schemes is that you basically hide your data behind noise. So you have your raw data, you add some random noise to it that basically hides the true data. Then you do these computations in such a way that the noise does not grow out of bounds. And finally, when you have the result, you can decrypt it by basically removing the noise again. And of course, the challenge is that this noise that you add will grow with the algorithmic depth. So the more operations you do with your encrypted data, the noise will start to get bigger and bigger. And this is what is called, that requires what is called bootstrapping. That's a process that basically made homomorphic encryption really interesting in the first place, maybe about 10, 12 years ago, is to basically remove some noise during the computation so that in theory you can have arbitrarily long algorithmic depth. If you want to know more about the CKKS scheme, I really recommend this Open Mind blog. It has a 5-part series on how to use and how to implement actually the CKKS scheme, and it's a good read for non-cryptographers. Just be aware that it needs some considerable math, so it's not for the faint of heart either. All right. So what are the basic building blocks for homomorphically encrypted algorithms? Well, everything is a vector, and you can add them, you can multiply them element-wise, and you can rotate them. So I think add and multiply is pretty self-explanatory. Rotate means basically, in Julia, it would be the circ shift function, so you can just rotate it in the order, and that's it. You also get multiplication or operations with plain text values, so you can also have a ciphertext added to a plain text value, also to a plain text scalar, and you have the bootstrapping operations. So these are all the tools in your toolbox that you have to build your algorithms, and that, of course, is a pretty severe limitation. For example, what you can already see, what's missing is something as simple as a division. So this is already a hard problem. If you want to do something like a sine function or some other nonlinear function, usually you have to somehow model it with a polynomial or something like that. There are a couple of efforts to bring homomorphic encryption to Julia. Ramparts is the first one that I found, but basically when I started to become interested in homomorphic encryption, it was already not active anymore, or didn't seem to be active anymore. There's the PHE package by Brian Thorne from 2020, and the toy FHE project from Keno Fisher, which I think was really just a toy problem also. In 2021, I tried for the first time to work with this in Julia by wrapping the C library, but really the effort I want to talk about today is with OpenFHE and SecureArithmetic that started basically around half a year ago together with my student Arseniy. So what is the idea behind these packages? OpenFHE is an open source homomorphic encryption library written in C++. It's basically a successor of a number of pre-existing libraries that somehow made the, in my opinion, very good decision to join forces and try to develop one powerful library instead of 5 less powerful libraries. OpenFHE.jl is then obviously a Julia wrapper for this library. We have like an intermediate stage, this OpenFHE Julia, which basically provides the C++ bindings using the CXS wrap package. And then we have SecureArithmetic, which is sort of a convenience package, add some syntactic sugar for rapid prototyping. So the OpenFHE library is written by cryptographers, and while it is considered to be production ready, it still requires a lot of knowledge on how to use it correctly. And SecureArithmetic, the idea behind it was to take some of these this ugliness, let's say, of having to write a code out of it and make it nice. And if you want to add 2 vectors, you just want to write plus. You don't want to write, I don't know, add eval something something something, right? All right. So before we get to the results. In practice, if you want to do a secure numerical computation, you need to set up a secure context. Originally, when I planned this talk, I thought I would be showing a lot more details on how to use this actually in Julia. But then I figured that if I want to show this in a meaningful way, I have to explain so much of the cryptography behind it that I basically will just skip most of this now. If you want to learn more about it, I really recommend to have a look at the SecureArithmetic package, where you can see a very simple example of how to use or how this code would look like in practice. Here, just a few words. If you want to do a secure simulation, or a secure computation, you need to set up a lot of parameters up front about problem size, encryption scheme. You need to decide up front what kind of multiplicative depth you want to support. And in the end, you need to make sure that you choose your parameters wisely, because they strongly affect both the accuracy of your results and the performance of your computations. In this case, I put some of the most important parameters here in the table on the right. I think the key takeaway here is that we use a security level of 128 bits. So technically, one could consider all these computations we did as cryptographically secure. Again, with the caveat that I'm personally not a cryptographer and that I just trust the library authors, in this case OpenFHE, that they actually really know what they're doing. All right, so let's have a look at accuracy and performance of some fundamental operations. Maybe before we go here, maybe one more thing. So the ring dimension here, 2 to the power of 17, means that our vectors are essentially of size 2 to the 16. So we always have 64,000 real values in each vector that we're doing the operations with. Now, later we're going to look at some results where we only have, let's say, 100 or maybe even less values that we actually work with. And you're wondering correctly, why would he use a 64,000 element vector if he only needs 40? Well, the problem is if you want to have the security, the accuracy, and the multiplicative depth, you have basically no choice. It ends up that the ring dimension must be 2 to the 17. So that's one of the hard facts of using homomorphic encryption. All right. So let's have a look at some fundamental operations and see how they affect accuracy and performance. So the first one is basically a simple, I have a vector of values, I encrypt it, then I decrypt it, and then I look at the results. On the left-hand side, you see the number of encryptions and decryptions we perform and how it affects the infinity error. So basically, we're looking at the maximum deviation of the true data, and we see we're here well within, let's say, double precision. So that seems to be okay. But we can already see here on the right-hand side in terms of time it takes, and also that we're here already talking about seconds or sub-second time. So this is not a very fast thing we're talking about. And it only gets worse from here. So yeah, just take this with you. What is also can be seen here is that the actual performance depends on the multiplicative depth. So having algorithms that have a longer multiplicative depth means also that typically all the single operations you're doing take more time. You can reset the multiplicative depth with this process that I described before, bootstrapping. But as we see, bootstrapping also does not come for free. All right, so encryption, decryption, okay, that's fine. Now let's have a look at addition. When we add, the blue line here is if we add 2 ciphertexts, we see that we also have an error, let's say, still on the order of double precision. And we also see that the time is, 10 to the minus 2 seconds is a little bit better than encryption, decryption, but it also grows strongly with the multiplicative depth. Now we look at multiplication, and multiplication is actually the thing that is the most problematic for homomorphic encryption schemes, because those are the ones that really make the error grow, and these are the ones that restrict the algorithmic depth. So sometimes it's called also just multiplicative depth, because this is what is restricted in fully homomorphic setups. And as you can see now, when we go to a number of multiplications larger than 14, we can see that the multiplicative error starts to skyrocket. So here we are, I would say, leaving the double precision realm already. So just by doing multiplications, we introduce a lot of, or we introduce maybe, depending on our application, a non-negligible error. And we can also see, if you do this with a multiplicative depth of 27, something like this, a single multiplication will take 1 second of compute time. So this is, again, not a cheap algorithm anymore. Now, I also introduced the rotate function as a third basic operation. Here, everything seems to be okay. The error is on the order of a double precision accuracy, and time. It's also not for free. So it apparently is not just rearranging some data, but it actually needs to recompute a lot of things behind the scenes. Now, finally, the elephant in the room, the bootstrapping algorithm. So as I said before, we need bootstrapping if we want to have a fully homomorphic scheme, so being able to have algorithms of arbitrary depth. So there's no way around it. But if you can look at the left graph, you can already see this is a whole different beast in terms of accuracy. So a single bootstrapping operation introduces an error of 10 to the minus 6. So we immediately lose basically half of our accuracy if we use bootstrapping with this set of parameters, with this specific library, but this is what is basically state of the art at the moment. And if you look at the time for a single bootstrapping, you will also not be much happier, I suppose, because a single bootstrapping with this setup now can easily take 30 to 60 seconds. So this means, coming from a person who's mostly involved in high-performance computing, using fully homomorphic encryption is not for the faint of heart. Here's also a table that basically summarizes the difference in errors and times and puts it relative to the addition, but I'll just skip over this. And now immediately proceed to the example that I actually want to show. So my background is in computational science, mostly computational fluid dynamics, or primarily computational fluid dynamics. And the problem that we wanted to look at is a simulation, a numerical simulation. And we, of course, picked the simplest example we could find. So we do a linear advection problem. These are the differential equations here that we're using. So once in 1D and once in 2D. If you don't know anything about linear scalar advection, it's not such a big issue. Just you see there are some values there, and we somehow want to solve this. We want to solve these equations in a numerical way. So we actually use two different schemes for this, and this is now basically where everyone who doesn't know about partial differential equations or numerical methods can now basically join in again. So this is basically an algorithm. In this case, it solves the advection problem, but it could be any other algorithm, and we just write it as we see it. So we have two numerical schemes, a first-order scheme and a second-order scheme. The second-order scheme is more accurate in general, but of course also more involved computationally. So you can already see that the equation 4 is much longer. And now we want to code this up using a homomorphic encryption scheme. And as I said before, what we now need to do is we need to take this mathematical formulation. This is equation 5, here in this case, for the Lax-Wendroff scheme, for the second-order scheme. And we now need to put it in a fully homomorphic encryption formulation. And in this case, it's actually not that hard. So the only change we really need to make is here where we have the UI. We can just take our regular vectors, and then we use the circ-shift function if we want to use a vector that is shifted. And by this, we can basically combine this in a smart way to get back our original formulation as basically as a vector formulation using these homomorphic encryption primitives. And this is the only part of Julia code that survived my slide revisions, and I just wanted to show it that you can see. So really, that's basically what our effort with SecureArithmetic was. It basically looks like the mathematical formulation, so it's now amenable, I would say, to experimentation and rapid prototyping. All right. Some results before I'm finished in a few minutes. This is now the result for the 1D problem. So we had a sinusoidal wave. We used both numerical schemes to let it run for basically one full period, such that it ends up basically where it started. It's a periodic problem. And as we can see, in this case, I think we used something like 40 points to discretize the whole simulation. So of this 64,000 value vector, we only used basically the first 40 values to do the actual computation, which is overkill, but also if we want to have 180-bit of security, the only way we can do it. As we expect, the exact solution and the second-order scheme, they're nearly indistinguishable, so I don't know if it's visible from back there, but the orange and the green curves are more or less on top of each other, whereas the first-order finite difference approximation is much more dissipative and obviously cannot capture the solution very well. what we can take away from this is that for a problem like this, our error of 10 to the minus 6 that was introduced by the bootstrapping algorithm apparently is not such a big issue. We also did the 2D simulations, but you cannot see much quantitatively here, but it's a similar story. The first order scheme is very dissipative. The second order scheme is in the eyeball norm indistinguishable from the exact solution. We also did a convergence analysis to make sure that we actually do have implemented proper schemes. If you're not a numerical analyst, you can skip over this slide, but what we can see here is that we get the expected first order of accuracy for the first order scheme and the second order of accuracy for the Lax-Wendroff scheme, both in 1D and in 2D. Now, some error analysis and some performance comparisons. So this is on the left is for the 1D problem, and the right is for the 2D problem. This compares now the cryptographically secure computation with the same computation using only plain text values. So the idea here was that one idea of secure arithmetic is that you can not just run your simulations using cryptographic algorithms, but we have actually different backends, and one backend is an unsecure, unencrypted backend. So you can basically prototype your algorithms, write them down, check the results, make sure everything works, and then you can just switch the backend to the encrypted one, and now you have to wait, of course. But you can basically do the prototyping without having to wait for all the machinery to run through. And what is interesting, I think, here to see is for the first n steps, we basically don't see any errors, because this is when the bootstrapping has not yet been called, right? So in the beginning, on this scale, 10 to the minus 6, our error is still in the order of 10 to the minus 12, so you don't see it in this graph. But once the first bootstrapping kicks in, the error jumps up, and then you can see it somehow goes down a little bit, and especially in the 2D scheme, it's I think, very interesting to see. The error seems to, let's say, recuperate a little bit over the iterations, but then you have a next bootstrapping, and then it jumps up again. So this seems to be how such a scheme behaves in practice. Now, finally, for the performance analysis, we see something similar to what we expected before. Let's only have a look at the left slide here, at the left figure here. The green curve is for the second order scheme, the blue curve for the first order scheme. The first order scheme obviously is cheaper because we have less numerical operations. That's what we expect. And we can also see that the runtime significantly increases each time we have a bootstrapping. So these are the little jumps, basically. And interestingly, the runtime seems to be going down the longer we go down the chain in terms of multiplicative depth. So the first few operations after a bootstrapping are rather expensive, so the slope is rather steep. And then once we get to the end of the permissible algorithmic depth, it somehow levels out a little bit, and then of course we have to hit another bootstrapping, and the time jumps up again. All right, final slide to summarize. With fully homomorphic encryption, we are able to perform more or less arbitrary algorithms over encrypted data. There are some severe practical limitations in terms of complexity, especially in terms of runtime, but also in terms of library support. You basically rely on libraries that someone else provides, and there's no way, at least for me, to fix anything or to add anything to that. In Julia, we have now the ability to do simple experimentation with fully homomorphic encryption using the SecureArithmetic package. And from my point of view, I would say secure numerical simulation is feasible, also for someone who is not a cryptographer. Whether it's practical, whether it's useful, well, that remains to be seen, but that's what I call research at the moment. And yeah, with this, I would like to stop here. Thank you, everyone, for your attention. And yeah, if there are questions, I'd be happy to try to answer them. Thanks.
Thank you, Michael. Yeah, let's take the time for 1 or 2 questions. So one up here by a different Michael.
Yeah, exactly. Yeah, thank you, Michael. I think it's a great talk. Very nice exploratory work, I would call it. So I have plenty of questions. I'm just going to ask one for now. For your benchmark, how did you actually choose the values? Like in the sense of, did you avoid causing issues of errors from the numerical floating point computations themselves? Like, is the error we see there only the error of the holomorphic encryption?
What do you mean with the benchmark? You mean the problem that we computed or the setup of the encryption scheme?
The basic setup when you're just checking the individual operations, addition, multiplication, and so on.
So basically, the values that we use here in this table on the right-hand side, these were optimized for accuracy and sanity. As I said before, the ring dimension basically was fixed once we set which security level we want to have. And this the scaling modulus, 59 bits, basically dictates the general accuracy of your scheme. So if you have a higher scaling modulus, you can get higher accuracy, but then you also need a higher ring dimension. But then the highest ring dimension that the library currently supports with 128-bit security is 2 to the power of 17. So it's sort of the sweet spot of being able to do this in a secure manner with, let's say, non-negligible multiplicative depth. There are probably a few values you can fiddle around with here, but for what we would try to do, there was no other way to configure this. And maybe just as a second, so this obviously is not a standard application for fully homomorphic encryption. So probably many would have expected here to see something about secure machine learning, which is probably the primary driver for this kind of technique, because there you only have multiplications and additions and maybe some activation functions if you have a neural network that you want to compute. We didn't try this yet, but there I think you can get some better results.
All right. Since lunch is waiting for all of us and we're a little bit over time, let's. Oh, do you have a quick question? Oh, come on. Let's take it. Let's take it. Lunch can wait for 2 more minutes.
Thanks for the talk. I'm just curious about, in terms of the efficiency comparing between decryption, encryption versus evaluating the circuit. How do they compare? In terms of the order of magnitude?
So the encryption decryption is more or less for free in comparison to evaluating the algorithm or the circuit on encrypted data. If you look at the actual runtime that you would require to do this on your machine in an unencrypted way, then nothing beats that. Okay, so I mean, if we look at the plain text execution times here, okay, so this takes like 150 steps. This takes like 0.03 seconds. I can't even encrypt my data in this time. Okay, so this is obviously not relevant, let's say, if you're just interested in the results. So this is basically the first proof of concept that you can do things like that, and whether it makes sense, that's to be found out.
Sorry, I was just asking about the execution time for ciphertext and versus the encryption, decryption, and
I'm not sure. So maybe we can just discuss this afterwards. I'm not sure.
All right, then let's stop here. Let's thank Michael and all the speakers of the session again.